Good morning, all. Last class we have seen informal design guidelines of database design. Today's class will be seeing fundamentals of functional dependencies, and later we will see how to design database schema with minimum redundancy. Functional dependency is a constraint between two sets of attributes from the database. Let R be a schema with n attributes and a functional dependency denoted by x determines y between two sets of attributes x and y of R, where x and y are subsets of attribute of R, satisfies a constraint on possible tuples in relation state R of R. The constraint is that for any tuples T1 and T2 in R that have T1x is equal to T2x, they must also have T1y equal to T2y. That means if the two sets of tuples agree on x values, they must also agree on y values. This is a constraint to be satisfied. Then you can say a functional dependency x determines y hold over that relational schema. We'll see with some examples also. X determines y says that y component of a tuple R are determined by x component, or in other words, y is functionally dependent on x. That's the meaning of a functional dependency as x determines y. X determines y in a relational schema if and only if whenever two tuples of R agree on x value, they must necessarily agree on y value. Consider this example. Let there are four attributes a, b, c, d and four tuples having value a1, b1, c1, d1. First tuple a1, b1, c1, d2, a1, b2, c2, d1, a2, b1, c3, d1. A, B determines C. Let be this a functional dependency, whether this functional dependency is violated or not. The first tuple and second tuple, the A, B value is A1, B1 as same value, x value is same. Then what's the y value? Y value is C1. What about the remaining tuples? Remaining tuples A, B value are not the same. Therefore, only when this constraint violation or not will be checked only if two tuples having the same value. Then the requirement is the y value should also be the same. In this relational instance, given relational instance, A, B determines C is not violated. Is not violated. Okay. What if A1, B1, C2, D1 is added? A new tuple, let be A1, B1, C2, D1 is added. When a new tuple is added as the fifth tuple, then three tuples are having the same values. That is the A, B value, A1, B1 for the first tuple, A1, B1 for the second tuple, and for the fifth tuple also A1, B1. In that case, first two tuple, the y value, that is the C value, is C1. For the last tuple, the y value is C2. Therefore, when the new tuple is added, what happens? When new tuple is added, the FD AB determines C is violated. Resulting instant would violate AB determines C. By looking in, therefore, what you can say, by looking into relational instance, we might be able to tell that a certain functional dependency does not hold. We can never reduce to a conclusion that FD does hold by looking at one or more relational instance of the relation, because FD, like any integrity constraint, is a statement about all possible legal instances of the relation. Therefore, from a relational instance, given relational instance, what you can say is whether an FD is violated or not. You cannot say whether FD hold, because there can be other possible legal tuples. Only if all the legal tuples are given, then only you can say this FD is violated or not. If X is a candidate key of R, does FD X determines Y, where Y is any subset of attribute of R? What is your answer? Let X is a candidate key of R. Does FD X determines Y, where Y is any subset of attribute of R, hold or not? Answer yes, because when X become a candidate key, no two tuples of the relation, any legal relational instance, will have the same X value. Since there is no same x value, the violation condition will never occur. That is why x determines y will hold if x is a candidate key. Yes. X determines y in R. Does y determine x hold in R? Answer is no, because x determines y means the x value determines y value, and y determines x means y value determines x value. Therefore, these two are not the same, therefore not equal. Another example, suppose that we have the following three tuples in legal instance of relation R A B C 1 2 3 4 2 3 5 3 3. Which of the following dependencies does hold over relation schema R? A determine B. What is the A value? These tuples. A values are 1, 4 and 5. These are not the same. Therefore, A determines B is not violated. What about BC determines A? BC determines A. BC, the first tuple BC value is 2, 3, second tuple B value is 2, 3, third tuple 3, 3. Therefore, first and second tuple BC values are the same, x values are the same. Then what about the y value? Y value is 1 and 4, A value is 1 and 4. Therefore, BC determines A, the FD is violated. B determines C, B values are 2, 2, the y values are 3, 3, then x value 2, 2, y value 3, 3. Therefore, it is not violated. Therefore, out of the three FDs, BC determines A is violated, other two is not violated. Inference rules for functional dependencies. Let F be a functional dependency hold over relational schema R. However, there can be numerous other FDs hold in legal relation instance that satisfies the dependency. Those other F dependencies are inferred or deduced from FDs in R. FDs in F. Formally, the set of all FDs that include F as well as all dependencies that can be inferred from F are called closure. Therefore, what is closure means? Given a set of FDs, you can infer some other FDs. Therefore, the set of all possible FDs, the given FDs plus those which are inferred, together known as closure. Consider this example. Let R be a relational schema, employee name, employee number, date of birth, address, D number, D name, D manager, E number. And the FDs, set of FDs hold over R are E number, E name, date of birth, that is E number determines these four attributes, D number determines these two attributes. Given these two FDs, you can have some other FDs like E number determines D name, or E number determines D manager E number, or D number determines D name. These are other possible FDs. That is, therefore, given these two set of FDs, you can have other inferred FDs together. The entire FD set is known as the closure. Therefore, finding out the closure is actually a difficult task. Now, what is Armstrong axioms? Let F be a set of FDs hold our relation schema R. Let X, Y and Z denote set of attribute our relation schema R. There are 3 Armstrong axioms plus 3 inference rule, total together 6 inference rule. These are known as Armstrong axioms. The first one is IR1, that is inference rule 1. If X is a superset of Y, X determines Y. The axiom says like this: X is a superset of Y, or Y is a subset of X. You can say X determines Y. That is the first rule, which is known as reflexivity. Second rule is known as augmentation. If you have in FD X determines Y, then XZ determines YZ for any Z. That is augmentation. Given an FD, you can have one more attribute or a subset of attribute set, so that XZ determines YZ. Augmentation. Third inference rule is transitivity. That means if you have x determines y as an FD and y determines z another FD, if we have these two FDs, then what hold x determines z. That is a third rule which is known as transitive. These three are the basic Armstrong axioms. And IR4 decomposition rule. Therefore, the entire six is also known as Armstrong axioms or inference rule. What the decomposition rule says that if there is an FD, x determines y z. Y z is what? Attribute sets. Y z. Then we can say x determines y and x determines z. Decomposition. That is on the right hand side. The attribute set are the x determines individually that attribute sets. Union, similarly IR rule 5 is union. If x determines y and x determines z, then we can say x determines y z. That is union of. There are two FDs, x determines y and x determines z. You can have another FD, x determines y z. That is a union rule, inference rule 5. And sixth rule is pseudo transitive rule. If x determines y is there, y and y wy determines z, x determines y and wy determines z is there, then you can have wx determines z. This you can infer. Therefore this is known as the six rules: reflexivity, augmentation, transitivity, decomposition, union, pseudo transitive rules. Theorem: Armstrong axioms are sound. That is in that way, in that they generate only FDs in F closure when applied to a set of FDs. Therefore, sound means when Armstrong axioms are applied on set of FDs, it will generate only FDs in F closure. They are complete in that repeated application of these rules will generate all FDs in F closure. Therefore, Armstrong axioms when repeatedly applied, we can generate closure. Therefore, sound and complete two words. One is they will generate only FDs in F closure. Complete means by repeated application you can generate all the FDs in the closure set. Proofs of Armstrong axioms. First rule is reflexivity. If x is a superset of y, then x determines y. That is what the reflexivity rules mean. Consider if IR1 says that attribute always determine itself for any other subset, which is obvious. IR1 always generate dependencies that are always true, hence it is known as trivial functional dependencies. Proof: suppose that x is a superset of y, that two tuples t1 to exist in relation instance of R such way that t1x is equal to t2x. For example, consider an example: employee relation, employee number, employee name, salary. What this FD says or what this rule says is that employee number, employee name and salary together determine salary. That is, employee number, employee name, salary is three attributes. Salary is a subset of attribute. What is a obvious or a trivial functional dependency? You have a set, a subset, another subset. For x, y, z is set of attribute. X, y, z determines x. X, y, z determines y. That such type of rule is known as reflexivity rule or the IR1. First, that is obvious. If there is two tuples with x, y, z value, then x value should also be the same. There is nothing in that. IR2 says that by adding same set of attribute on both left and right side of dependency result in another valid function. That is, if there is a x determines y, then you add a third attribute z on the left as well as right, result in a valid functional dependency. That is what can be proved by contradiction. According to IR3, functional dependency is transitive. That is, if there is x determines y, y determines z, then you can have x determines z. That is what the transitive rule says. Remaining IR inference rules can be proved using IR1 through IR3. That is, by the application of IR1 to IR3, remaining three IR rules can be proved. What is the fourth one? Decomposition. Decomposition rule is x. There is an if there is an FD, x determines y z. Then what you can say, x determines y and x determines z. This is the fourth rule or the decomposition rule. For the proof for that by using the other first three IR rules. Given x determines y, so that is what given. Then using the IR1, that is the reflexivity property, you can say that yz determines y because yz is a superset, determines a subset y, that will valid. Therefore, what you can say, x determines yz is given and yz determines y. What is the meaning of that? X determines y. Using IR3, you can say x determines y. Similarly, same rule is applicable for x determines z also. Same way you can prove that x determines z is also. That is, x determines yz is given, yz determines y using the IR1. Then from the 2, by application of IR3, what is the transitive rule? That is, x determines yz, yz determines y. Therefore, you can say x determines y. Similar way, you can say x determines z also. Therefore, this is what the proof of IR4 decomposition rule. IR5 union. X determines y, x determines z. Union rule is x determines y z. Proof for that. Given x determines y, given x determines z, these two are given. Then x determines xy y by using IR2, that is augmentation of x, augmenting the x determines y with x itself. Therefore, xx is x itself, xy. For that, you got x determines xy, and xy determines yz using applying IR2 on with y. If you augment with y, what will be? Xy. Xy determines augmenting this second IR2 on second one, xy determines yz. From these two, what is can say? X determines xy, xy determines yz. That is why you will get x determines yz. Therefore, proof is very simple. By augmenting initially with x, then with y, you will get two other rules. By application of that transitive IR3, you can prove that x determines y. That is a union rule is proved. Now, zero transitive rule, you have x determines, this is bit complicated to understand. You have an FD, x determines y, another FD, that is the right hand side with another attribute w. Y, wy determine z. Then what you can say? Wx, this right hand side, w determines, wx determines z. A pseudo transitive rule. That is, you have x determines y and y with another attribute. That is, wy determines z. Then you can say that wx determines z. Given x determines y as well as given wy determines z. These two are given. Then by applying IR2 in one, what you can do? W, if you apply w, wx is equal to wy. Then wx is equal to z. From these two, you can say wx by augmenting wx. From these two, what you can say? Wx, wy, wy. Therefore, wx is equal to wy determines z. Wx determines z. From these two, you can say, applying IR3 on 3 and 2. 3 is this one, 2 is this one. Therefore, from this one, for wx determines z. This is what the rule says. So far, what I have seen is functional dependency. What is functional dependency? And 6 rules. Armstrong axioms, IR1 to IR6, and proof of the 6 also. 6 out of which 3, 4, 5, 6 we proved. Now, using this, you can find a closed set of attribute under F. X is an attribute, F is functional dependency. What it says is, we know Armstrong axioms IR1, 2, IR3 are sound and complete. Sound and complete. That sound means by the application it will generate only FDs in the closure, and complete means by repeated application it will generate all the FDs in the closure. And how to find attribute closure? Attribute closure means given a set of FDs, you want to find out the closure of an attribute. When we see some examples, it will be more easier. The algorithm says like this: algorithm determining X closure given a set of FDs F. Initially, X closure is X itself. Then you'll just store the X closure value, the current value to old X closure. For each FD, Y determines Z in F. You have gone with a set of FDs. Let Y determine Z is an FD in the set. If X closure is a superset of Y, then we will add this Z. That is, X closure now become the current X closure union Z until X closure is equal to old X closure. That is, until there is no change, we will add each FD one by one. Initially, the FD is the attribute itself. Then, for every FD, if the closure set, the current closure set contains that left hand side, we will add the right hand side too. That's all. And this process will be repeated until there is no change. With an example, we will see how to find closure set of an attribute. Example: consider the FDs. E number determines E name. P number determines P name, P location. There is a bracket also. E number determines E name. P number determines P name, P location, and E number, P number uh, together determines hours. Okay, this is a let be set contains three FDs. E number determines E name, P number determines P name, P location, and E number, P number together determines hours. From this one, F closure, the closure of F can be determined by using IR1 and IR3. Using the above algorithm, you can find out E number closure. What is E number closure? E number is just added, then that currently that will contain E number. That is why the E name will also be added. Look into the other FDs given. Will any left hand side be in this one? No other left. This is P number. This is E number. P number is not the set. Therefore, we will check with verify with each of the other given FDs whether the left hand side is having that FD left hand side. Sorry, the the current closure will be is having that left hand side. If so, the right hand side will be added. In this E number case, you have only these two attributes in the closure of E number. Now P number closure. P number will first add P number, then we will be adding P name, P location, because this is an FD. Any other FD will come to that? No other FD, because this is E number, this is not in this one. E number, P number, this is not in this one. Therefore, we cannot add. Now another one is E number, P number. What is the closure? E number, P number, hours is added. Then because of E number, E name will come. Because of the P name, P location, P name and P location. Therefore, this E number, P name closure will be having all the attributes. This is very important. That is E number, P number together closure if you take, because there is an FD like that. If you take, then you will be getting all the attribute in that set. Consider another example. A relation schema R ABCD is set. Find the attribute closure of attribute from the set of FDs given below. C determines FDs. C determines D. C determines A. B determines C. Therefore, what is C closure? C closure is C will be added, then D will automatically come. Because of there is one more FD with that one, A will also come. What about B? B will not come. Therefore, C closure is C, D, A. What about B closure? B will be there, then C will come. Because of the A will come, and because of C, D will also come. Therefore, B closure will be containing A closure will be having C, D, A. It is simple. And B closure will be having B, C, then D, then A. What about this one? From this one, F2 is another set. A determines B, BC determines D, A determines C. What is A closure? A closure will be having A, then because of this FD, B will be added. Then because of A, C will also be added. Now it contains A, B, C. Because BC is in the closure set and BC there is a left hand side, for this FD, D will also come. Therefore, A closure will be having A, B, C and D. What about BC closure? BC closure is BC and D, and about BC and D, nothing more. Therefore, BC closure is BCD only. Okay, I think you get an idea what is it. Now we will see equivalence of set of functional dependencies. Given two sets of functional dependency, you have to say whether these two functional dependency sets are equivalent or not. Definition: a set of functional dependencies F set to cover another set of functional dependencies E if every FD in E is also in F closure. That is, every dependency in E can be inferred from F. A given a set of functional dependency F set to cover another functional dependency E. What you can say in that case? That is, if E closure is F closure, in that case you can say given two sets of functional dependencies, what is the requirement here is that if their closure is same, you can say these two functional dependencies sets are equivalent. Two sets of functional E and are equivalent if and only if E closure is F closure. Hence, equivalence means every FD in E can be inferred from F, or every FD in F can be inferred from E. That is, E is equivalent to F if both conditions of E covers F and F covers E hold. We'll see with an example. Given two sets of FDs, we want to say whether they are equivalent or not. If they are equivalent, what is the condition that will satisfy? The condition that will satisfy is their closure will be the same. Consider this relation schema A, B, C, D, and given FD1, A determines B, B determines C, AB determines D, and FD2, A determines B, B determines C, A determines C, A determines D. Are they equivalent? These two, FD1 is equivalent to FD2. How to check? The only way is, given FD1, what you have to check is you have FD1 as A determines A. These two are the same. Then AB determines D. This is an additional FD which is not in the FD2. Therefore, AB determines D as such is not in the FD2. But if you take AB closure in this case as well as in this case, if they are same, then we can say that you will check. What is the idea here is check which are all FDs in FD1 present in FD2. FD1, which are all FDs in FD1 are present in FD2. A determines B is present here, B determines C is present here. Only FD which is not present is AB determines D. That is the FD which is not present in FD2 are present in FD2. AB is not directly present. Check whether it can be derived using FDs in FD2. Therefore, in FD2, AB closure is, what is AB closure? AB closure. A closure is, AB closure is AB, C, and because of A, D will also come. That is, AB closure is containing A, B, C, D. That means AB can functionally determine A, B, C, D. That means AB can determine D. Therefore, it is inferred. Therefore, from the, what is the idea? Idea here is we will check whether the FDs in the first set is present in second set or not. First two are present as such. Third one is not present. Third one is inferred using the FDs in the second set. If you take AB closure, you will see ABCD, which means that AB can functionally determine A, B, C and D. Hence, AB determine D is holding in FD2. Therefore, this part is equivalent. Now we'll check whether the FDs given in FD2 is present in FD1 or not. Again, the first two are present as such. The third and fourth, A determined C, is not present as such in FD1. A determined D is not present in FD1. Therefore, we'll check whether the A closure will give C, A closure will give D. If it's so, it will work. Check whether step 2, check whether all FDs, this is step 2, check whether all FDs in FD2 are present in FD1. A determines B and B determines are present in FD1. And what about the other? A determines C and A determines D are not directly present in FD1. Check whether it can be derived using FDs in FD1. What is using the FD? What is A determines C? What is required? A determines C as well as A determines A. You take the closure of A. Closure of A is A closure is A, B, C, A, B, D. Therefore, A closure contain A, B, C, D. What's the meaning? A closure, A can functionally determine A as well as B as well as C as well as D. Therefore, the FD A determines C as well as A determines C can be inferred. Therefore, what you can say, these two functional sets FD1, FD2 are equivalent. Why? Because if you take the closure set, it will give the same set. Meaning, therefore, FD1 and FD2 are equivalent. Now we'll see, you have to practice, then only you can have a minimum idea of what is its equivalence or not. You'll be given with some exercises. This is, as far as examination point of view, this is very important. Equivalence will always ask. Most of the question paper you can see equivalence is asked. Now another idea which is known as minimal cover of set of functional dependency is set of functional dependency F such that satisfies a property that E is in the closure of F of F. This property is lost if the dependency from the set F is removed. If any dependency from the set is removed. Therefore, minimal cover of dependency E, set of dependency E, is a set of dependency F such that says property that every dependency E is in closure of F. Therefore, you are going with a set of functional dependency E. You have to find out another set F such that F closure will be containing all the functional dependencies in E. That means the F is a minimal set of functional dependencies. A minimal set. If one of the FDs in that minimal set is removed, then that condition will be violated. If you are gone with a set of functional dependency that may be containing redundant functional dependencies, then what is a minimal cover is you have to identify a minimal subset of FDs which will cover all the FDs given the original one. That is what requirement. Therefore, F closure will be containing all the FDs. Therefore, you will be keeping only the minimum set of FDs required. That is what minimal. This is very important as far as the normal forms are concerned. Minimal. This is also a bit difficult to do with exercises. Properties of minimal cover. Every dependency in F has a single attribute for its right hand side. So minimal cover should have some properties. Every dependency, you cannot have X determines Y Z. You can have X determines Y, X determines Z. The right hand side will always be single attribute. We cannot replace X determines A in F with a functional dependency Y determines A, where Y is proper subset of X and still have the set of dependencies. Therefore, you cannot, that is X determines A in F, that is the F is our new functional dependency with a dependency Y determines A, where Y is a proper set of subset of X. That is, you have X determines A in F and you are going to remove a Y which is a subset, and still this work. Therefore, this condition imposes the constraint that this should be the minimum set of functional dependencies. We cannot remove any dependency from F and still have the set of dependencies in work. Therefore, these three are the conditions or properties of minimal cover. Every dependency in F has a single attribute for its right hand side. We cannot replace x determines a in f with a dependency y determines a where y is proper subset. That is, y is a proper subset of x. That is, from this one you are going to remove something, some matrix. X is something, let be x is ab, and you are going to remove b, a determines c. Then that is not. We cannot remove any dependency from f, and still the set of function dependencies is equivalent to f. Okay. There is an algorithm for finding minimal cover of for set of functional dependencies E. Minimal cover F for a functional dependence. That is, E is given, you have to identify F. Initially, F is E itself. That is, given set of functional dependency, the minimal cover is the given itself. Replace X determines A1, A2, AN in F by the f this x determines a1, x determines a2, that is, apply the decomposition rule. For each x determines a in f, for each dependency present in f do, because f is your e, for each attribute b that is an element of x do, what to do is f minus x determines a union x minus b. Therefore, b is a subset. Therefore, what you are going to do is, with some examples it will be more clear. This is very simple only. F is your set of function dependency minus x determines a, that is, you are removing a function dependency x determines a from the set, and by including another set. For example, you have a function dependency ab determines c. You are going to remove ab determines c from the set, and instead of that a determines c is added. That is, you are trying to eliminate one of the attribute on the left hand side, because left hand side is a multiple attribute. What you are trying to do is, you are going to remove one of the attribute that is present in the left hand side and check whether still the closure is the same, or still it works or not. For f minus x determines a, x determines c is an fd, it is being removed. Instead of that, what you will add, you are going to add x minus b determines a. That is, you are trying to remove an attribute b from the function dependency x determines a. Okay, if so, it is equivalent to f. Then replace x determines a with x minus b determines a in f. That is, you are trying to remove x determines a with an x minus b. You are trying to remove an attribute b for each attribute in the element. Therefore, for each attribute b that is an element of x, you have to do this again. For each remaining fd's, if all such attributes from the left hand sides are removed, for each remaining fd's x determines a in do, what you can try to do is f minus x determines a is equivalent to f. That means, first you are trying to remove an attribute from the left hand side. Now by this step you are trying to remove an fd itself from the step. Still the closure is the same. Therefore, the algorithm is very simple. First one is right hand side, if there are multiple attributes, apply decomposition rule. Second one is, for each of the fd, if the left hand side is a multiple attributes, try to remove each one of the attribute on the left hand side, and still it works or not, check. And third rule is whether you can remove an fd as such, x determines a from the set, and still this dependency is covering or not. Therefore, this is the minimal cover. We will see an example, then it will be more clear. Remove x determines. Consider this set of fd's. A determines bc, b determines c, a determines b, ab determines c. Find canonical cover. This is not minimal cover or canonical cover. A determines bc. Therefore, by applying the first rule, what is the first condition? A determines bc. This should be apply a decomposition rule. What it become? A determines b, a determines c. Then b determines c, a determines b already in the set. Therefore, what is a new set of fd's? A determines b, b determines c, a determines b, and ab determines c will be the new set of attribute. Apply the first step. Let all right hand side be single attributes. Now FDs are A determine B, A determines C, B determines C, AB determines C. Now check whether B in AB determines C is extraneous. Now you have an FD, this one, left hand side having multiple attribute, whether this B or A is extra. That is what you want to check. What is AB closure? AB closure contains AB closure, we will try to find AB closure and A closure. You are trying to eliminate B. If AB closure and A closure are the same, both are ABC. Hence B can be, B is extraneous. Therefore, a simple rule is you try to remove B by applying what AB closure from the AB closure, both are hence B in AB determines C is extra. That is A determines C only. That is only what we required. Remaining FDs are now A determines B, A determines C, B determines C, and B is removed. Therefore, A determines C is already there. Therefore, that become these three FDs only. Now, from this one, what you can say? A determines B and B determines C. A determines C. Therefore, which one is extra? Because A determines B is there, and you have a B determines C also there. Then, do you require this A determines C in this set? This is not required, because this is by applying transitive rule you can find. Therefore, this FD itself, this is the third step. Therefore, this is the first step. This is second step. This is third step. A requires C is extra. Therefore, what is minimal cover here? Minimal cover is A determines B and B determines C. That's all. Therefore, minimal cover or canonical cover of the given set of FD. Therefore, you have a set of FDs. From that one, we find out what is the bare minimum set of FDs. For A determines B and B determines C are the minimal cover of this set of FDs. Therefore, three steps. First step is apply decomposition rule. Second step is check whether an attribute is extra. Third, check whether a FD itself is extra. Therefore, with this we'll stop at this point. Therefore, today's class we have looked into what is functional dependency, and second, Armstrong axioms, 6 axioms we have seen and proof of that also, and we check whether given two sets of function dependencies are equivalent or not, and finally minimal cover. Minimal cover is again the minimum set of function dependency from a given set. Okay, thank you.